Any questions?
Yes. So are we gonna have any problems that have force not constant for chapters? Do we have to practice them? Do you think?
Anything where a force is not constant, it would be discrete still. I would not give you, force. Force is modeled by 5t squared minus 3t plus 2. I mean, that's a calculus-based problem.
Yeah.
So,
Do we have any of them?
I don't think so.
Okay, because there's videos on it, but I didn't see them on the master slides.
Yeah, some of the videos should be listed that they were for 251, or at least there should be some comment over, from here to here, this is the 151 material.
Okay.
Yep.
Yeah.
Variable acceleration requires calculus, usually.
Yeah, that's all.
Other questions? Today is the 3rd. Okay. Masters is up. All right. Then, let's start talking about harmonic motion. I guess what we're about to talk about is has a variable force as well. However, we will bypass the calculus. All right, so let's talk about, we have harmonic motion. So primarily we'll deal with simple harmonic motion. Actually, let's talk about waves first off. There are two basic kinds of waves. Longitudinal and transverse. Your textbook, I don't think, gets into it. Most textbooks seem to leave it off, but occasionally there are textbooks that talk about surface waves. And so I'm going to bring them in here just for completeness. One other thing, we're talking about waves here, we're talking about mechanical waves, as opposed to electromagnetic waves. Oh, we can do it with 6 people. Let's do a transverse wave, but it does require everyone participating being with. I'm going to need you to stand up in just a moment. Wait on Laura to stop.
Sorry.
Okay, we're going to start over here, and I guess since you're in front, what's going to happen is Luisas and Laura are going to stand up. Feel free to do the flare with the hands if you want. Are going to stand up and then down, and then you're going to do up and down, and then you're going to do up and down, like in a stadium. All right, whenever you two are ready. Man, it's like watching those videos, and we got thousands of people. For those who miss it, who can't see it on camera, it was incredible. Can't believe we missed that. That's a transverse wave. Now, which way did the wave move?
To the right.
Okay, that way. But you, as the mediums of the wave, the thing that was actually the particles that were moving to create the wave, you moved up and down, but the wave moved this way. So in a transverse wave, the particles move perpendicular to the motion. Now, given this absolutely incredible definition here, what would be a longitudinal wave?
Particles in parallel motion?
Yeah, or anti-parallel. Yeah. So an example of that, if I take the slinky, grab a couple more coils up top. All right, so if I release some of the coils, is that easier to see there or against the white?
White.
The white. All right. So if I release, calm it down, release some of the coils, you should see something move throughout the whole thing. What did you notice? You are talking so quietly right now.
I don't know.
It moved along the length of the slinky.
Yeah. So you saw something bounce all the way down, go all the way down to the bottom?
Mm-hmm.
All right, for those who missed it. That was not as good a demonstration.
Yeah.
So you see something move all the way down. Now, in reality, the particles, the coil, just moved a little bit, moved down and then it moved back up. But it pushed another one, which pushed another one, which pushed another one. This is a longitudinal wave. Particles move, I'll write parallel, but it could be moving in the direction of the wave or opposite direction of the wave. Parallel to, particles move perpendicular to, oh, that should be wave there. Wave. Now, some examples of these.
Why is it not in motion? Why is it wave?
Because in the case of the transverse, in both cases, but for specifically the transverse, it was the wave that moved this way. I guess I perhaps was starting to write motion of wave, but,
We could write that.
pardon?
We could write motion of wave.
Yes. Let's see if this is working today. Not particularly. So an example of a longitudinal wave, sound waves are longitudinal because your vocal cords are vibrating back and forth. They hit air molecules, which hit air molecules, which hit air molecules. In a longitudinal wave, it requires one particle to hit another particle, which causes it to go bounce off. And you have a whole bunch of, at that level, perfectly elastic collisions as one particle bounces into another particle and so on. Example of transverse wave, we'll call it the stadium wave. Battle ropes. I think that's what they're called, the exercise thing, the battle ropes?
I have no idea, but I know what you're talking about.
Okay,
Me too.
all right. Anyone know the name of them? We're gonna go with battle ropes for right now. Now, we're about to exhaust my knowledge of geology. There it is. So if you have Earth, if there's an earthquake over here, and I've got my seismograph over here, and they're fancier than this now. My wife did some research summer '88, I think it was, somewhere around there. And she was looking at seismic data as they were creating the Bat Creek, in the Bat Creek project, which was, basically they were setting up a dam with a turbine. They would fill it with water during low energy use times, and then when they needed a sudden burst of energy, such as middle of summer when the air conditioners are already hot, you quickly release all the water, change that potential energy into kinetic as it goes through, turns the turbine, creates electricity. So we were there while they were doing the construction, and so there was regular times in which they would do blasting, and my wife was looking at set up seismographs at various places around the area. And the way she did it, she had this, basically this drum, about yay big, with paper on the outside, on the paper, and you smoke it so that, as in you hold it over a flame, it gets all black. And so as it turns, there's a needle etching the black off. And so when there's an explosion, things are vibrating, and you'll see a white hind and then something like that. That's what that drawing is supposed to represent. I suspect you'd be hard pressed to find those anymore. But still, it's what's in my head. All right, so there's an earthquake on the other side of the world, and you get waves being sent over here. Now, there are two types of waves that are produced. There are longitudinal waves and there are transverse waves. So the first waves that hit here are longitudinal waves. So the primary waves that hit the seismograph are longitudinal waves, and so, which also can be referred to as pressure waves, because again, it's one thing hitting another, hitting another. So these are, another example of a longitudinal wave is a P wave. The second waves to get there are the transverse waves, sometimes referred to as shear waves. Now shear, if I have go back to the slinky, an incredibly useful toy. Shear would be a sideways force which causes deformation in an axial direction. Anyway, a sideways direction. So shear waves or secondary waves, otherwise known as S waves. Now, part of the reason for that is they move slightly different speeds as they go through the Earth. But another factor, a rather major factor in terms of figuring out how the Earth is made, is that transverse waves require, as one particle gets moved, it drags the next one with it. So it requires that one particle can pull on the next one. Well, if you think about air, if I do this, how many of you are feeling that? Because as an air molecule moves, it's not dragging the next one with it. And so transverse waves really need a solid. You need a solid for a transverse wave to move. Longitudinal waves can move through solids or fluids. And when I say fluid, that's gas or liquid. So goes through solid, liquid, gas, plasma, etc. Transverse waves really need a solid. And so by doing the math, figuring out how fast these waves travel, you eventually get to the conclusion that the core here is not solid. It does not count out the idea of, I guess, Edgar Rice Burroughs. There's a society inside the middle of the Earth, the Hollow Earth Society. I think there's still people in that camp, but I always associated with Edgar Rice Burroughs. Questions here? All right, surface waves. The nice, simple, ideal surface wave is that the particle is not moving perpendicular or parallel. It's actually a combination of the two, that it moves in a circle. So a particle moves in a circle as the wave moves that way, and then the next one will move in a circle and so forth. That's the classic ideal. It's just a combination of these two. And I haven't seen it in a textbook for a while, but I assume they're still out there. All right, so how do I actually represent these waves in terms of drawing them on the board? Well, the transverse wave is fairly simple. if I am producing a transverse wave, I would just draw sort of a profile of it. So my transverse wave, if I had, say, a battle rope and I was going up and down like this and watching the waves go down and back, my transverse wave, I would just draw something like that. And that's a physical representation of what I'm seeing. But longitudinal waves are a little bit more mysterious in the fact that, take sound for example, how would I represent a sound wave? Because in reality, what you have are these areas of higher than normal density. And I will make reference to air molecules, even though I know air is not a molecule, it's just air molecules in reference to molecules in the air. So I'll have these points where I have a whole bunch of particles together, and then these areas where there's fewer particles than normal, followed by another area where I've got higher density. This here is known as compression. Particles are closer together than normal, and this is rarefaction. I've been pronouncing it that way for decades. I'm assuming that's correct pronunciation. So a sound wave is just a series of compression and rarefaction, but if I wanted to represent a sound wave, representing it like this is going to be a real nuisance to have to write that over and over again. So I would represent it, well, like this. This would be the points where I've got high pressure, the points where I have low pressure. High pressure, low pressure, high pressure. So I'm still going to use the same symbol. There are cases, though, in which it's more convenient really to do an overhead view. If I throw a rock into a still pond and you get the ripple coming out of it. That's another way of representing it, where I would do the high pressure is the point where I've got a line, and a line, and a line, and then in between I have the low pressure. So this would be like peaks on some waves. So all of these can represent waves, whether this is transverse, any of these could be longitudinal. Whatever is just most convenient to get across the idea.
Which is transverse?
Excuse me?
Which one is transverse?
Transverse would be the top one. Because you physically have a wave, something that's moving up and down.
But the particles are moving with the wave, right?
The particles are moving up and down like this as the wave moves that way or that way.
Oh, I thought that was just the way of representing the particles in the air. Like,
This would be particles in the air, although I could represent this looking like this as well.
oh,
I will use this drawing to represent either type of wave. But if I'm doing a transverse wave, I'm going to be doing sort of that side view. Since we're talking about waves, we need to get some other vocabulary down. That's who doesn't like starting every section with some vocab. And the once it's been said once, all of you know the vocabulary. We never have to revisit it, because that's the way learning works. Some of the words we've done before. Some of it's not new vocabulary. Period. We talked about period before. The symbol used for period is a capital T, and it is the time to create one cycle of repetitive motion. Frequency. And part of it is vague, I know, but The symbol I use for frequency is the same symbol I use for friction. Now, if you're looking in textbooks, especially the more advanced textbooks, they will use a different symbol for for frequency. They will use the Greek letter nu. In some fonts, it looks like that, like a V that's been caught in the wind. Some textbooks, it looks more like this, which looks a whole lot like the V's. So, if you think about that, so let's talk about speed. What's the basic formula for speed?
Distance by time.
All right. So if I'm creating a wave over and over again, well, in the time it takes me to create a wave, that wave is going to move a certain distance. So if I went up and down on a rope, I have this, whatever I've done is being propagated along it. And the amount of distance that is traveled and the time it takes me to create a wave is known as the wavelength. We're going to connect it back to that in just a second. The symbol for wavelength is a lambda. Using the usual clever, it's a length. What Greek letter starts with an L? Ah, lambda. So this would be the distance a wave travels in one period. So the speed of that wave would be, so this would be the wavelength divided by the period. Frequency is how often something, it's how frequently something happens. More specifically, it is the number of oscillations per unit time. So